Do chemical leftovers from the early Earth sit near its core? Let's take a journey into the depths of the Earth, down through the crust and mantle nearly to the core. We'll use seismic waves to show the way. Since they echo through the planet following an earthquake and reveal its internal structure like radar waves, down near the core, there are zones where seismic waves slow to a crawl. New research from the University of Utah finds that these enigmatic and descriptively named ultra-low velocity zones are surprisingly layered. Modeling suggests that it's possible some of these zones are leftovers from the processes that shaped the early Earth. Welcome to Science Unmasked. Please subscribe and turn on the notification button so you can get our latest videos. Remnants of incomplete mixing like clumps of flour in the bottom of a bowl of batter. Michael S. Thorne, associate professor in the Department of Geology and Geophysics, said that of all the features we know about in the deep mantle, ultra-low velocity zones represent what are probably the most extreme features found anywhere on the planet. Into the mantle. Let's review how the interior of the Earth is structured. We live on the crust, a thin layer of solid rock. Between the crust and the iron-nickel core at the center of the planet is the mantle. It's not an ocean of lava, instead it's more like solid rock, but hot and with an ability to move that drives plate tectonics at the surface. How can we have an idea what's going on in the mantle and the core? Seismic waves. As it rippled through the Earth after an earthquake, scientists on the surface can measure how and when the waves arrive at monitoring stations around the world. From those measurements, they can back calculate how the waves were reflected and deflected by structures within the Earth, including layers of different densities. That's how we know where the boundaries are between the crust, mantle, and core, and partially how we know what they're made of. Ultra-low velocity zones sit at the bottom of the mantle, atop the liquid metal outer core. In these areas, seismic waves slow as much as half, and density goes up by a third. Scientists initially thought that these zones were areas where the mantle was partially melted, and might be the source of magma for so-called hotspot volcanic regions like Iceland. However, Professor Thorne pointed out that most of the things we call ultra-low velocity zones don't appear to be located beneath hotspot volcanoes, so that cannot be the whole story. So he and his team set out to explore an alternative hypothesis, that the ultra-low velocity zones may be regions made of different rocks than the rest of the mantle, and that their composition may harken back into the early Earth. Professor Thorne believes that perhaps ultra-low velocity zones could be a collection of iron oxide, which we see as rust at the surface, but that can behave as a metal in the deep mantle. If that's the case, pockets of iron oxide just outside of the core might influence the Earth's magnetic field that is generated just below. Reverse engineering seismic waves. To get a clear picture, the researchers studied ultra-low velocity zones beneath the Coral Sea, between Australia and New Zealand. It's an ideal location because of abundance of earthquakes in the area that provide a high-resolution seismic picture of the core mantle boundary. The hope was that high-resolution observations could reveal more about how ultra-low velocity zones are put together. But getting a seismic image of something through nearly 1,800 miles of crust and mantle isn't easy. It's also not always conclusive. A thick layer of low-velocity material might reflect seismic waves the same way as a thin layer of even lower velocity material. So the team used a reverse engineering approach. Pachai said that they can create a model of the Earth that includes ultra-low wave speed reductions and then run a computer simulation that shows what the seismic waveform would look like if that is what the Earth actually looked like. Then they would compare those predicted recordings with the recordings that they actually have. Over hundreds of thousands of models run, the method called Bayesian inversion yields a mathematically robust model of the interior with a good understanding of the uncertainties and trade-offs of different assumptions in the model. One particular question that researchers wanted to answer is whether there are internal structures such as layers within ultra-low velocity zones. The answer, according to the models, is that the layers are highly likely. This is a big deal because it shows that the way to understanding how these zones came to be. Looking back at the origins of the early Earth, what does it mean that there are likely layers? More than 4 billion years ago, while dense iron was sinking to the core of the early Earth and lighter materials were floating up into the mantle, a planetary object about the size of Mars may have slammed into the very early Earth. The collision may have thrown debris into Earth orbit, and that could have later formed the Moon. It also raised the temperature of the early Earth significantly, as you might expect from two planets smashing into each other. As a result, a large body of molten material known as magma ocean is formed. The ocean would have consisted of rock, gases, and crystals suspended in the magma. The ocean would have sorted itself out as it cooled, with dense materials sinking and layering onto the bottom of the mantle. Over the following billions of years, as the mantle churned and convected, the dense layers would have been pushed into small patches, showing up as the layer ultra-low velocity zones we see today. Pachai said that this finding changes scientists' view on the original and dynamics of ultra-low velocity zones. This type of ultra-low velocity zone can be explained by chemical heterogeneity is created at the very beginning of the Earth's history, and that they are still not well mixed after 4.5 billion years of mantle convection. Not the final word. The study provides some evidence of the origins of some ultra-low velocity zones, although there's also evidence to suggest that different origins for others, such as the melting of the ocean's crust that's sinking back into the mantle. But if at least some ultra-low velocity zones are leftovers from the early Earth, they preserve some of the history of the planet that otherwise have been lost. This discovery provides a tool to understand the initial thermal and chemical status of Earth's mantle and their long-term evolution. That's all from Science Unmasked. Remember to subscribe and like our videos and share it with your friends.